So let's begin our discussion of the thickness of foil's lab. A foil is a very thin piece of metal. And of course, metal, a pure metal, of course, is metallically bonding with itself so that its atoms are arranged in different crystal lattices. Some will be face-centered. The ones we're dealing with in lab are going to be face-centered. And we're going to be working with our calculations that we've been doing in class. So we're going to use those to try to find how many atoms tall our foils are. So we're going to go through calculations that we've been using in class. We're going to use our conversions, and we're going to be using mole concept. And by doing so, we're going to figure out essentially the height of atoms in these thickness of foils. So let's begin. So I give you a bunch of information. The most important here is that I give you lattice constants, okay, or atomic radii, or the densities. All right, and I'm going to give you two different metal foils, aluminum and copper. And from those, we're going to compare and contrast the differences in the height of those atoms in that foil. So here's the procedure, but let's go right to it. Okay, and we're going to do this twice. So you're going to see in my data table, I have a repetition of the metal foil, number 1 and number 2. So what you do for aluminum, you'll do for copper. So let's start, and assuming you're going to be measuring copper first. All right, so let's write copper, Cu for cuprum. All right, some point here. Okay, so we got my copper. And the density of the metal is, we're going to use the values that I provided because I want us to work on our conversions. And if you notice, copper has a density of 8,920 kilograms per what? Ooh, meter cubed. So 8920, let's write that down. Okay, now 8920 kilograms, okay, per meter cubed. That's not a unit we're going to be using here. Now let me explain what we're trying to do. We're trying to find the thickness of this foil, which we're going to have a tough time measuring. We're going to measure the mass of the foil. We're going to put the foil on an electric scale, electric balance, and it's going to give us grams. Okay, and we're going to determine the volume of the foil through density. Let's talk about what that means. We know that density is equal to mass over volume. And so we're going to solve for this volume. So we should be able to manipulate this equation. So what we want to do here is solve for the volume. And algebraically, if you solve for the volume, you're going to get V is equal to the mass divided by the density. And that's just using some simple algebra. One quick way is to exchange the top to the bottom, but using your algebra, you should be able to rearrange this formula to volume is mass over density. And that's what we want to solve for. And there is a reason why I want to solve for that, because we're going to measure the mass, okay? We already have the density, so we already have, okay, we already have the mass, we already have the density. We're going to solve for the volume because we're trying to solve for the thickness. And let me explain. The thickness, well, what do we know? Volume has 3 dimensions, right? So the volume is equal to length times width times the thickness, okay, or height, however you want to think about it. The height of the foil, we'll call it thickness, T, okay? And so we're going to solve for that volume by using our density value, and we're going to actually measure, okay, the length, and we're going to measure the width, okay? So we're going to solve for the volume here. We're going to measure the length. We're going to measure the width. We should be able to solve for the thickness. Another algebra, okay? And when we do so, just keeping this the same, we're going to get the thickness, okay, is equal to the volume divided by the length times the width. And you're going to be solving for the thickness. We want that thickness to be in centimeters. Okay, so that's what we're doing. Okay, so to understand that, we can't use the density that's in kilograms per meter squared because we want to be in what? We want to be in centimeters. So we're going to have some conversions here. And also we're in grams. So if you notice, my volume unit and my mass unit are different. Okay, so to get centimeters, all right, I'm gonna have to convert. So let's do that. Let's convert. Let's convert our density, and I'll help you with that. 8,000. Okay, 8,920 kilograms over a meter cubed. Okay, I'm going to get rid of kilograms. Kilograms go on the bottom. I'm always using my units. What do I know? Kilo means 1,000. So there's 1,000 grams per 1 kilogram. Okay, and now I've got grams per meter cubed. Now, we talked about this in class, okay, that there is a million, and it's up here, okay, there is a million centimeter, should be a cube there, equals 1 meter cubed. So that's a conversion, and that, we talked about that in class. So for every 1 meter cubed, there's 10 to the sixth centimeters cubed. And notice I set this up and I put the meter cubed on top to get rid of it. And lo and behold, I'm timesing this by 1,000 and dividing by a million. And what that gives me is the value I need to solve for. Of course, it gives me 8.920 gram per centimeter. Hey, I can use that here, right? Because what's the formula here? The formula is the volume is equal to the mass that I measure, which is going to be in grams. Don't forget, what I measure is going to be in grams, okay, all over the density that I just converted, which now is in what? Grams per, grams per centimeter cubed. Okay, so it's grams per centimeter cubed. Now, for those, again, simple algebra, we're using a lot of math and simplification skills here. How does this cancel? Okay, for those that don't know, and I'm going to rewrite it over here, volume is equal to grams over centimeters cubed. That's what we're doing here when we solve for this using the right units. For those that haven't figured that out, these grams cancel, and what I'm left with is 1 over centimeter, which, by the way, you should recognize that equals centimeter cubed. Okay, and that's what we're after. So we had to convert. Okay, don't forget we're going to measure this. Okay, and those that are doing this virtually, I will have foils that have their mass and their length and width measured. So we're also going to have to measure the length and the width, okay, because now once I have, all right, the volume, which I could calculate now, okay, once I have the volume, using the mass that I measure, I don't have that now, so I can't calculate that. But once I have that, I'll have the volume. Okay, so solve for V, take your mass that you measure, divide by the density that we just converted, and this will be this value here. Now, once you have that value, you're going to what? Measure the length and the width. Okay, you're going to use the value that you got, that you calculated here in the first equation. This is the first equation. Well, this is the first equation here. And then you're going to do this a second time for the second equation using that volume that you got here, okay? And using these measured values, you solve for t. So I guess this would be really my second equation right down here. Okay, so measure these two values, solve for t, and that should give you, of course, centimeters. Okay, and why? Well, if you look carefully, volume is what? Centimeters cubed over what? Hey, a length is a centimeter, and then I'm going to times that by a centimeter, and that gives you centimeters squared. So centimeter cubed over centimeter squared, okay, is going to give you just centimeter. The units must make sense, and that's where we get our thickness. And you say, Mr. Grotsky, why we just measured with a ruler? Well, for those that are doing virtually, okay, these squares of foils are so thin that we could not accurately measure, okay, a thin layer, okay, with the ruler. It's too thin. Okay, we could use something called a caliper. All right, we'll talk about that in class or outside of class about that. So that's how I get my thickness, and I should be able to do that with a metal, aluminum, and copper. And of course, Those that are doing virtual, I'll have those measurements for your review, already measured to use them. Okay, now the next step is what a lot of my other class is picking up from. Hey, what's the atomic radius? So we go back to the values given. So for copper, I'm going to use atomic radius here for copper as 0.128 nanometers. Now, nanometer, of course, is a billionth of a meter, which means there's 1 times 10 to the 9 of them, okay, nanometers, tiny little values, equals 1 meter. Now, that's given to you in the top anyway, so we're going to use 0.128, 0.128. So you're just going to write that, 0.128 nanometers. Okay, diameter, well, that's easy. You're going to take that 0.128. If that's the radius, diameter is what? Okay, twice as big. All right, so you're going to times that by 2. And that gives you the what? The distance through the center of, or the length or height of that atom. Remember, the point of this lab is to find the atoms tall. Now, I want you to convert the nanometer into a centimeter. Okay, now the diameter is 0.128, okay, times 2, right? But the unit is nanometer. And of course, to convert, we're going to get rid of nanometer. I like going directly to the meter. Okay, the meter is a bigger unit, bigger number, and I'm sorry, the smaller unit gets the bigger number, right? So this would be 1 times 10 to the 9. It's a billionth. And you need a lot more of something smaller than you do of something bigger. Okay, so that gives me meter, and I know that a meter and a centimeter differ by 100. For every 1 meter, notice I'm putting meter on the bottom because, hey, it's going to cancel. I'm using my units and my conversions here, equals 100 centimeters. And that'll give me my value for the diameter in centimeters. Okay, that's pretty straightforward. You probably didn't need me for that. And now number 9, number of atoms stacked one another in thickness. So remember, we have this very, very thin foil, okay? And how many atoms high is it, okay? That's what we're going to do here. Now, we're going to make an assumption. I know when you assume, you make a donkey out of you and me. So we're going to make an assumption here that these guys stack right on top of each other, that all of the atoms do. So number 9, we're going to do that assumption that, hey, forget everything we learned about simple unit cells. I want you to stack them on top of each other, okay? Just to do that. Now, what are we doing? We're stacking the diameter on top of another diameter, on top of another diameter. So I'm saying, okay, how many atoms tall is your foil in copper? In this case, you'll do it for aluminum, okay, knowing that the diameter has a certain centimeters, has a certain value of centimeters. Well, how do you do that? How many atoms? Well, it's a division problem, right? Think about that. We have the total thickness in centimeters, okay? That's a total thickness in centimeters, all right? And we know that each what? Single atom has a diameter in centimeters. Okay? And so, party people, you're going to take that total value in thickness, which is going to be much, much bigger than the individual atom. And basically, by doing the division, you're going to find how many atoms tall. Okay? And you can round that off to the nearest atom. All right? And that will give you a sense of how many atoms tall it will be if they do stack on each other. And we're going to do that right there. Okay, now number 10 wants to know the height of a mole of atoms. Let's say there was a mole of atoms that stacked. That means how many of these atoms with their diameters, how tall would it be? So if I had not just 3, I had 6.02 times 10 to the 23 number of metal or copper atoms in this case. Okay, what would be the height of a mole of atoms stacked on each other? So wait a minute, you know the height of one. Okay, the height of one is its diameter. Okay, so it's its diameter that we've just filled. Now we're going to keep everything, we had everything in centimeters. Notice I want that in meters. So you should be able to convert the diameter into meters, get rid of centimeters to go back to meters, and we should note that every one, there's 100. Hey, you notice centimeters are smaller, bigger number. So we take our diameter, convert to meters. Great. Okay, whatever value that is. So now we have this height of one atom in meters. Well, guess what? I don't want one of them. I want the equivalent of a mole, which is really what? It's equal to 6.02 times 10 to 23. So we're going to take that height and we're going to times that by the meter, okay, value of the diameter. We're going to have that many. So how tall would our thickness of our foil be if we had a mole of atoms stacked on each other? That will surprise you, okay? And then number 11, I want you to calculate the lattice constant. Okay, now how do we do that? Well, party people, if you notice, you say, I can just look it up. I gave me all this data. So we go to copper and we notice, oh my gosh, Mr. Grodsky, you did not give me any aluminum or copper data, although you did give me the atomic radii. So this is a lot like a problem we've done in class. Because I'm telling you copper and aluminum both are face-centered cubic structures, we know that we've got this face in the middle, and then we have these eighths, okay, at the corner. And I'm not really good at drawing. Okay, so we have, I can just do this like this, and we have this scenario here. And what do we know? That we know that this is a radius, this is the second, third, fourth radius. So we know that this hypotenuse of this right triangle is what? 4r. And there's my 90-degree angle, and here's my sine. And these are 45-degree angles. And what we know is the sine of 45 is equal to the opposite. Now, the opposite value, whether it's this one or this one, it doesn't matter, are both going to be what? The height, the width, it's going to be the dimension of the cube, which is all the same. So I'm looking for the lattice constant, and we've seen this before, over the what? 4 times the radius. The radius, of course, is given to us in that table. So we should be able to handle that calculation. All right, make sure you understand that this is in nanometers, so you're solving in nanometers as well. And that's easy. And then number 12, last one. What is the new height of atoms considering the lattice constant value? Now I want you to think about the fact that, hey, they don't really stack on top of each other. They stack on top of each other by unit cells. So put another unit cell here, okay? And I want you to think about how tall would it be now, okay? So with another unit cell that stacks on itself, make sure you understand that we're using face-centered cubic, okay, structures. They're both aluminum and copper face-centered. I want you to think about, all right, how many atoms high would it be now when you consider that they don't stack up nice and neatly like we did here. They stack up based upon the arrangement of their crystal lattice in a face-centered cubic structure. That I'm not going to help you on. That I need you to think on your own and come up with a value. Okay, you'd be surprised there. All right, and you're going to do the same thing for aluminum, except of course you're using a different mass. It's going to have a different length and width. It's going to have a different density, a different atomic radius, but everything is done the same. And when you completed that, put all those values that you just calculated into this table, and then answer these questions where I'm asking you to compare and contrast. And then one last calculation, I want you to calculate the density of silver. Remember, density is mass over volume using the lattice constant. So we're going to, but what? We're going to use a face-centered cubic structure for silver. We should know how we're doing the mass of how many atoms if it's face-centered. Hey, and the volume is the dimension of the face-centered cubic structure, and you have the lattice energy. So we've done this calculation, okay, already. And that essentially is the lab. Okay, so again, for those people that are doing it virtually, I will have some copper and aluminum that you can measure or have measured for you in front of you in order to calculate this. I hope that is clear enough for you, and continue on. Good luck.